In this video, we're going to tackle a very important concept, namely the ways in which we take samples. This opens up an area of statistics that will later lead us to the central limit theorem in the next video, and subsequently to ideas and concepts like hypothesis testing. Okay, so let's start with a general overview of what sampling involves. In the background, we're going to have a population in the sense of a set of members of the population. These could be people, these could be transactions, these could be securities. And a population is basically all the members of a certain group. Like CFA Level 1 candidates, you form a population. Now, based on the population, we may compute so-called population parameters. For example, the mean, the standard deviation. So the mean is denoted by the Greek letter mu. I exaggerated this little tail here. Sigma is the Greek letter that denotes standard deviation. So let's say this is the mean of the population, and this is the population standard dev, standard deviation. Okay. So these are quantities that we can compute which describe the population. However, sometimes we're forced to take samples from that population. And a sample is going to be obviously less than all the members of a group. We're going to see methods for selecting samples from the population and why we do sampling. And based on the observations, the data in the sample, we will be computing so-called sample statistics. And these are measures used to describe the samples, just like parameters describe a population. So over here, population parameters are quantities, metrics, quantities computed to describe a population. To describe the entire population. On the basis of data contained in a sample, we'll be computing sample statistics. So these are quantities computed to describe the sample naturally. A given sample, for example, X bar or S. This is the sample mean. So the mean computed based on the data in the sample. S is the sample standard deviation, and you'll see these symbols appearing later on as well in subsequent videos. Why is sampling important? Because we often use these sample statistics to make judgments about the population. We don't have necessarily access to the whole population, or it may be too costly, too time consuming to test the whole population or measure everything in the population. So we can use the data computed on the basis of the sample statistics, to make judgments, conclusions, or as we say, inferences about the population can be used to make inferences. This is a branch of statistics known as inferential statistics about the population parameters. So basically these things which remain unknown. However, because we are making or basing our inferences on a sample, on a selection, this introduces an element of potential error. So sampling introduces what's known as sampling, or exposes us to sampling error. And, this is an inherent part of inferential statistics. It's something that cannot necessarily be avoided, can be managed. And it's always the case of, if I had the time and the money, the resources basically, which are costly, I could go and try and measure the whole population, right? But I don't necessarily have the resources to do it. So I'm stuck with working on a sample, and that introduces the sampling error. And there's a trade-off that you have to be, you have to appreciate its existence, right? Now, let's just ask the question, why sample in the first place? Well, like we said, very often it's just not going to be feasible to examine every member of the population. So maybe we cannot observe or even identify and examine every member of the population. It would just be impossible to do so. Or even if it were possible, it would be inefficient, economically to do so. Too costly, too time consuming. Once again, back to the idea of time and money. Okay, on to the actual sampling methods now. These fall into categories. One is probability sampling. Probability sampling, it's going to be the bigger of the two in terms of our discussion. And the second is non-probability sampling. Right. What happens over here? Basically, every member of the population from which the sample is coming has an equal chance of being selected and included in the sample. Has an equal chance of being drawn or selected for inclusion in the sample. And this may, there is no guarantee, but this may or can result in a sample which is representative of the population. Doesn't have to, but it may. Or by doing things this way, you're definitely increasing the likelihood that this will happen, right? And this, once again, in turn, may result in greater accuracy, reliability of that sample and anything we do based on it. And in just a moment's time, we'll start examining these methods. They will include something called simple random sampling. then stratified random sampling, and another one which is kind of slightly outside the two main methods. So these are the sort of the main ones, and you also have to understand something called cluster sampling. Now, for the non-probability methods, this is where you consider factors other than probability. Factors other than probability, i.e. giving every member of the population an equal chance of being selected, are considered. And these will be things like convenience. So e.g. convenience, that's a possible factor. What's available, essentially, accessibility of data. Accessibility of data, that is data concerning the members of the population, or judgment, the researchers or samplers' own personal judgment, which often stems from experience. Now, this may result in a sample which is not representative, in a non-representative sample, more so than it is with probability sampling. And methods we'll be examining, at least briefly, are convenience sampling, and the second one is going to be judgmental sampling. So that's judgmental sampling. Okay, so that's the outline of what we will be spending the rest of the video on, starting with these three methods and then moving on to these subsequent two. Okay, let's start off with those probability sampling methods. And the first one on the list was simple random sampling. Let's recall that this is the method where each member of a given population, that was a characteristic or a feature of probability methods or probability approaches. Each member of a population has an equal chance of being selected. And this specific approach, the simple approach, is going to be particularly useful or applicable if the population from which that sample should be drawn is homogeneous, in the sense that all the members share pretty much the same characteristics. So let's say you want to do a study of income, earning, salaries among CFA candidates, and you want to, let's say, do it in a specific country, let's say Switzerland. And to make the population even more homogeneous, let's say, yes, e.g. all CFA Level 1 candidates in Switzerland. So we've already narrowed it down by country. We could do it even more, could go down to city level or some other administrative unit, geographical unit. But, we said all level 1 candidates, because I'm assuming there could be a difference between level 1, level 2, level 3 candidates. The assumption being, as the further you go in the exams, the more perhaps you are earning. Well, let's hope so. Let's hope that's the case generally. So if you wanted to do such a study, you would take the list of all CFA level 1 candidates. I'm guessing you had access to this. Every member of the group would have an ID, and you would randomly select, I don't know, a simple random sample of 50 candidates, level 1 in Switzerland, and you would poll them about their earnings and compute and draw some inferences from that simple random sample. Okay. There's a special case of simple random sampling that you should know about. And that's systematic sampling. And it's used when you cannot really identify all the members of a population. So used when all members of a population cannot be coded, i.e. assigned a number, an ID, so as to then subsequently randomly select specific IDs for inclusion in the sample. So if we can't identify them all, we can't code them. Perhaps we can't even identify them all. I mean, think about something like, well, not CFA level 1 candidates in Switzerland, but perhaps ants in a forest, you know, the little insect that you can find everywhere, including a forest. How can you identify all the ants in a forest? Let me write this down. Ants in a forest. No way. They can all be tagged and identified and then randomly selected. So instead of this, we would probably, as a solution, we would identify every cave member of the population. So every 5th, every 10th member that walks by. So you see lots of ants as they walk by. You take the 10th one, the 20th one, the 30th one for every cave, e.g. every 10th member, until you get a sample that is good enough in terms of size, until a sample of the required size is achieved. And later on, when we talk about the central limit theorem in the next video, you'll see what the relevant size may be. Okay, now that's pretty much it on simple random sampling. I just want to make a couple of comments, which your curriculum also makes at this juncture, at this point. And it's to do with the notion of sampling error. We talked about sampling exposing us to the risk of error. This is obviously the risk that there is going to be a discrepancy between what the population parameter is, e.g., you know, the true mean, for example, versus what you compute on the basis of the sample, where on the basis of the sample you can compute a statistic, e.g. a sample mean x bar, as opposed to the true value. But obviously the idea behind sampling is we do this because we want to, on the basis of the sample mean, try to make inferences about the true value of the parameter. So we're supposed to, this is supposed to be this is used as an estimate of the true population parameter. But sampling error is that difference between this versus this. And what you have to realize, and this will later on be explored in quite a lot of detail, is that the sample statistic is itself a random variable. And we're going to have what we call a sampling distribution, once again explored in detail in the next video under the central limit theorem. And this is going to be a distribution of all the possible values which the sample statistic may take on, may adopt. So if this is a sample, if this is a, let me go back one step. If that's the population from which we take a sample, and on the basis of, let's call this a sample, on the basis of this we compute a sample mean, right? That's one sample that we could take and one mean that we could calculate. There could be another sample that we take of equal size, call that sample 2, and on the basis of that one we would compute a completely different or slightly different sample mean and other statistics. So the assumption here is, and I'm going to repeat that assumption in the next video as well, the samples that we're talking about would be of equal size. Size that is typically denoted as n, and obviously drawn from the same population. And if you sampled multiple times, always constructing or drawing a sample of the same size as before, you would get many candidates for X bar to be used as an estimate for your population mean. And the question is, how would they compare to one another? Maybe X1 would be here, maybe X bar 2 would be here, X bar 3 would be here. And as you do this many times, you'd get lots and lots of data to be plotted here. But as you'll discover in the next video on the central limit theorem, if you make the sample large enough, if you have a big enough sample, the distribution, the sampling distribution, takes on some very interesting and useful properties. The next method of sampling, once again sticking to probability sampling methods, is stratified random sampling. Somewhat more complex as compared to the previous one. So what's going to go on here? First of all, we're going to divide the population into subpopulations called strata. Strata is the plural, stratum is the singular form of this, strata. So these are subpopulations. And then we will, as step number 2, draw simple random samples, so the ones that we previously discussed, giving every member an equal chance of being drawn, draw simple random samples for each of the strata or stratum, I guess. Now, importantly, in proportion to the size of each stratum to the size of the population. You'll see what I mean in a moment. I'll show you a numerical example. And then, as step number 3, to finish things off, we will combine those simple random samples from the individual strata, combine the samples into a bigger sample, an overall stratified random sample. Which is going to include elements of all the samples based on those samples which are based on the strata. Those get combined into something more generic. Now, when is this going to be applicable or most useful? When you have a population which is not necessarily homogeneous. So when the population is not homogeneous, or in other words, heterogeneous, i.e. heterogeneous, meaning different as opposed to more or less the same. So continuing with that example of CFA candidates, let's say we've got a population which consists of all CFA, not just level 1, but CFA candidates in Switzerland, and we want to, like before, measure the mean or estimate the mean income that they generate, whatever. We, however, deduce that they probably should be split into strata, into subpopulations, reflective of which level they are studying for. Level 1, level 2, level 3, and because we probably have data concerning the size of each subpopulation, we'll know that there are 1,000 candidates here, maybe 400 candidates here, and just 100 at level 3. So the size of the overall population is 1,500, but we have also knowledge about the size of each individual level population or subpopulation. And let's say we want a sample size, overall sample, equal to 60, right? So how would we now split things and into substrata? For level 1, so strata, subpopulations, because the sample size we want to overall achieve is just 60, we would take the size of this stratum relative to the size of the overall population, so 1,000 to 1,500, which is obviously 2/3, and say, well, our overall stratified random sample should be composed in 2/3 of level 1 candidates. So the sample we're going to take from this group is going to be 2/3 of 60, which gives 40. And we will accordingly now do a simple random sample of level 1 candidates with a size n equal to 40. And once we select these guys, we'll put them into the overall stratified random sample. What about the level 2 stratum? Well, 400 in relation to 1,500. Once again, times 60. Let's see what that gives. It should give a nice normal figure, whole number, sorry. 400 divided by 1,500 times 60 gives, okay, a size of 16. So once again, 16 level 2 candidates will be sampled, or a sample of 16 candidates will be drawn from this overall subpopulation, or from this stratum. And the same goes for level 1, level 3, 100 divided by 1,500 times that same 60. So 100 divided by 1,500 times 60, we'll just have a sample of size 4. So from these 100 candidates, we'll sample just 4. Combining these into an overall stratified random sample with a size of 60. Now, what is the benefit of doing this? When you've got a varied, non-homogeneous population, you tend to retain in your sample those divisions, those subdivisions. They are preserved. So population subdivisions are preserved and therefore also reflected in the ultimate sample, in that stratified random sample, thanks to which you get greater precision or less dispersion, less variance of the ultimate population parameter estimates. Because remember, we're doing this, we're sampling so as to make conclusions, inferences, judgments, estimates about the true population values. So when you do this, you get greater precision, less dispersion of population parameter estimates, which is a good thing, greater precision or less dispersion variance. Now, a very important application of this in finance, other than studying CFA Level 1 candidates, is the world of bond indexing. So this is used in bond indexing, and that means constructing a portfolio of bonds or actually applies also to other securities, which matches or replicates the performance of an index which you choose. It's chosen by the portfolio manager. Now, this can be done in two ways, this bond indexing. One way, called full replication, or pure bond indexing will involve purchasing and owning every security included in the index. So hold all the bonds which are included in the chosen index. Obviously, also in the right proportions, in proportion to their weights. Because an index is not just a listing of securities, in this case bonds, it also gives you weights or proportions in which you should hold them. So if something is half a percentage point of an index, you have to also make sure that the money you've got in your portfolio, or its appropriate part, half a percentage point, is allocated to that specific asset, which is extremely difficult in the world of bonds. Ridiculously difficult. Why? Because bond indexes often contain thousands of securities. Bond indexes, or indices, may, not all of them, but many of them do, may feature thousands of securities, of individual bonds. And a lot of the time, trying to buy all of them in the right weights, in the right proportions, means you'd have to have a huge portfolio to start with so as to replicate the weights. But other than that, it's going to be very costly. There's going to be huge transaction costs involved. And many of these securities are very illiquid in the sense that buying them will cause you to suffer a huge bid-ask premium to convince somebody to sell them to you if they're not heavily traded. So instead, an alternative to this, and this is where stratified random sampling comes in, we use this approach. And instead of trying to hold every security, we start off by identifying or mapping the risk factors. So identify the risk factors, the factors that cause bond prices to change, that have an impact on bond prices. And these will typically be things like, if you've done some studies on fixed income, you'll probably already know this, the time left to maturity, whether the coupon is fixed or variable, and obviously who the issuer is. So issuer quality as quantified by a rating typically. And then what you can do is you can create strata. So basically say, ooh, here I've got my different maturities, securities up to 1 year, up to 2 years, from 1 to 2 years until maturity, 3 years, 4 years, etc., 5 years. Here I've got the different issuer qualities like, triple A, double A, single A. These are ratings. So you create little blocks like cells, like strata. And also, you have to add a third dimension in what I just drew here, because I talked about fixed or variable coupons. So for each one, fixed or variable, fixed or variable. And for each little cell here, which would be your subpopulation, you take a sample and pick a sample from each stratum, and just use that for your bond portfolio construction, instead of holding every individual member of the index. Pick a sample from each stratum, and obviously in the right proportion, put it into your portfolio in the proportions in which these strata are represented in the index. There is a nice example in your curriculum of this. I think it's example 1 in this relevant reading on sampling methods. So if you want to have a look at it. The third method is cluster sampling. This is L. So here we're going to be dividing the population. Population is divided not into strata, but into clusters. So if that's the overall population, clusters are going to be subsets of that population. So these, for example, could be, let's say you're trying to do some research and statistical inference about a whole city, and the clusters could be districts within a city. So let me just say that the clusters are often based on geography, as opposed to things like age or income or CFA exam level. So they could be things like city districts, maybe states within a country, or perhaps, I mean, the one I often think of is patients getting treatment in different hospitals. And around the country. And what will happen is these clusters will be treated by the researchers. They are treated as mini representations of the entire population, treated as a mini representation of the overall entire population. And what you'll do is select a specific cluster, typically randomly, or clusters, maybe this one and this one. So randomly select specific clusters. And then subsequently, and one of two things may follow. One is all members of that cluster or those clusters are then sampled. Included in the study. This is a one stage process, one stage cluster sampling, or two-stage clustering may happen, or two-stage cluster sampling, may take place, in which case, once you've got your identified clusters or cluster, so just like before, first step, randomly select a cluster or clusters, which is what we've done over here. That was the first step. And then once you've got your random selection, a specific cluster. Draw a random sample from the selected cluster. The difference being you'll include all the members of that cluster in your measurements over here, whereas here you'll still take a sample from that randomly selected cluster in the first place. Okay, it's an additional method that you should know about. So what's going to be some of the sort of upsides, drawbacks, and advantages of this method? Let's start with the advantages, right? It's going to be time efficient and also cost efficient, probably, to do things on a cluster basis as opposed to treating the entire population, especially when the whole entire population is large. So it would be difficult to include everything in the study. But the big drawback is only members of specific selected clusters are included, either fully or as a result of being potentially drawn in a sample. But if you were not belonging to a cluster that was selected, you're completely left out of the study. So that introduces the risk of error. So it lowers the accuracy of the method and any estimates that we draw from it, because a single cluster that was selected may not be representative of the entire population. Of course, quite obvious. The final group of sampling methods that we're going to discuss in this video are those non-probability sampling methods that I previously introduced by name, starting with convenience sampling. And recall that this is, in general, overall, non-probability sampling is not is a bunch of methods where we don't necessarily give every member of a population an equal chance of being selected. And here, the sample selection is going to be based on ease of access. By the person performing the study, by the researcher or sampler. Obviously, the drawback is the sample may, once again, not be representative of the entire population from which it is selected. But the very important plus or advantage of this method is that it's going to be quick and low cost. So because of that, you'll often find it being used in, for example, preliminary research, when you're just hypothesizing about an idea. And maybe you send a questionnaire to be filled in by those who are closest to you, acquaintances, those who you can easily access, or a smaller case pilot study. Small scale, not case, pilot study. And this obviously precedes potentially a larger scale, a more representative study based on a proper probability-based sample. Now, the second method is judgmental sampling. There's an E missing here, judgmental sampling. Sorry, over here I should have had sampling as well. So this is a method where the sample selection is, as the name suggests, is based on the researcher's judgment, their experience, their knowledge. Now, once again, a drawback. The sample may be affected by, the personal bias, some kind of skew of the researcher towards a certain direction. And once again, obviously, the sample may end up not being representative, may not be representative of the entire population. That's a common thing over here and over here for these non-probability methods. But it's a way of doing sampling, especially under conditions of time constraints, so useful under time constraint conditions. One place in finance where you'll see this being applied is not necessarily time constraint, but certain speciality cases where the judgment and experience of the sampler does potentially make this quite a good method. The example given in your book is auditing financial statements. Auditors, when they audit financial statements, they often do it on a sample basis. So, for example, they don't check every trade receivables line or trade creditors, trade payables item. They take a sample to check on that sample whether the figures are correct, whether they can be confirmed. And they often do this sampling, this selection based on their judgment, on their experience. Same with inventory, right? If you want to audit a company's inventory, you wouldn't go and check every item and count it. You would select certain inventory lines, using your judgment to assess which ones are potentially tricky, most at risk. And this is where such things make sense, okay, or this method makes sense. Right, one more comment here, and then we're finished with this topic. It's not going to have anything to do with non-probability sampling. It's going to be more of a universal comment. And it's very important. Universal note. The sampling that we do must be done on the same population. You must draw samples from the same population. And, you may think, well, that's quite obvious, but it's not always obvious, especially when we're dealing with time series data. So when you've got data coming from different points in time, and your curriculum gives the example of investment returns, right, achieved by a manager over time. Well, what if the manager changed their strategy at a certain point in time? Then you cannot combine the performance before the change of strategy with the performance after the change of strategy, because they don't belong to the same population. In fact, what you should do is treat this as, let's say, population number 1, this as population number 2, and do your research on these populations individually. It wouldn't be all right to combine these. Another example, which I was just thought of, would be, what if you were to measure the time it takes to conduct a business meeting in the corporate world? Well, there was an important change that happened when COVID struck, right? A lot of the meetings that we previously had face-to-face became online meetings, and that surely affected the time those meetings take. So if you try to measure or sample meetings and measure their mean length, where in the sample you had meetings from before COVID, face-to-face meetings, and after COVID, which are online meetings, you would be essentially bundling together and combining two different populations. So especially in the case of time series data, so data coming from different moments in time, it's critical to identify. So we must identify certain important events which mark an ending to one population and the start of another. A change of the way we do stuff, like a strategic change, a change in a paradigm of some aspect of business or life.